Hello everyone and welcome to this video. Today we're gonna discuss the line integral and we're gonna go over some definitions and also we're gonna cover some related concepts and ideas related to the line integral. And so let's start with our definition. So this is our first definition here. So let F be a vector field with continuous component defined along a smooth curve C parameterized by R of t, where t is bigger than or equal a and smaller than or equal b. Then the line integral of f along the curve c is defined by this. And so what is this? This is basically the integral of c f dot t ds equals the integral of c is also equal, so f dot product f dot t, okay, which is basically f dot dr over ds. Okay, so these are all vectors. As you can see, this is a vector and this is a vector. dr over ds times ds, which is equals to f dot dr, which is a vector. And so these are all ways to define the line integral. And so in order to evaluate the line integral of f along the path c, we have a couple steps that we need to go through. And so our first step is gonna be to express the vector field f in terms of the parameterized curve c as f of r of t by basically substituting the components x equals b of t, y equals h of t, and z equals k of t of r into the scalar components m of xy and of xyz and p of f. And so we basically plug the function r of t inside the function of f. So r, let's say r composed, f composed r, or it's like composition. And then when we express the vector field in terms of the parameterized curve c, then we can find the velocity, which is the derivative vector dr over dt. And then we basically evaluate the line integral with respect to the parameter t, where t is bigger than or equal a and smaller than or equal b, which is going to be given. And so basically we get integral of c f dot dr equals the integral from a to b f of rt dot dr over dt times dt. So that's the way to evaluate it. Now, this can be done also for all of the components. So we have the component m, n, and p. These are components of f. And we are basically going to substitute r into f. As you can see, this is r. So it's all a function of t. And we're going to substitute it in f, basically. And by that we get multiple integrals, one of terms 1 with respect to x, which is mxyz dx, and which this, when we substitute the g n, this g of t is from r of t, and we substitute also h of t, and we substitute k of t. And also we have g prime of t, which is basically this part, dr over dt, and then multiplied by dt. So that's basically our x component of f. Okay, so the line integral of the x component And here we'll have the line integral for the y component, which is basically the same. We're gonna substitute, but this time we're gonna substitute in the y component of f. That's basically h prime of t. The same for the z component. And that's basically how we evaluate the line integral for different components. Now, let's take this definition. Now, we have a lot of definitions now, and we're going to go over examples now after we go through these definitions since they are important. So we're going to define the line integral. We're going to define also, we call it, yeah, the line integral. We're going to define the work, the flow, and the flux. And we're going to take a lot of examples. Don't worry about that. So let's see be a smooth curve parameterized by r of t. So this is our parameterized curve, and then t is bigger than or equal a, smaller than or equal b, and if be a continuous force field over a region containing c. And so the work the work done in moving an object from the point A equal r of A to the point B equals r of B, so these points will be given along the path C. It's gonna be basically this. And what this is just what we have here. And so we could say that the line integral of the work is just basically the integral of C f dot t, and you can say t is the velocity, okay? So it is the integral of f dot the velocity ds, which is basically from A to B, f of r of t dot dr over dt times dt. Now here you can see that this is basically what we did before, and it's basically the work defined. And so we already did define the work. Okay, so that is the work we apply. And so here are some examples. Let's just do these. So he wants us to find the work done by the force field, and this is the force field in moving a particle along the semicircle. So this is a semicircle r of t. Let's draw this semicircle. So cosine of t plus sine of t, say xy. And so this should look something. Yeah, so let's draw the sine and cosine separately. So now let's say here we have pi over 2 pi, 3 pi over 2, and 2 pi. Now the sine is just gonna be here, we have 1, the sine is gonna go here, it's gonna come down, it's gonna come up here and come back down. Now the cosine is like this, it's gonna go here, go down, and like this. And so when you add these, we should get something like this. Let's try to draw it using this mouse. Okay, so let's say this mouse. And so cosine of t, or let's say x, plus sine x. Okay. Okay, so that's interesting. So cosine and sine. Okay, so how are we going to draw this? It's interesting. I think we should try to use the t here. Okay, and so let's draw a table here. Okay, so t, we have here t, we have then cosine of t, and we have sine of t. And then let's say t is 0, t, this is how we do it, pi 3 pi over 2, and then 2 pi, and then we substitute here, and these are going to be just the x values and the y values. So x equals cosine of t. Okay, so yeah, that's how we draw it, and y equals sine of t. And now we just get our, well, that's easy, I don't need even a calculator. So 1 0, pi over 2 is 0 1, pi is negative 1 0, and 3 pi over 2 is 0 negative 1, and here is just 1 0. And so if we draw this, it's gonna be basically from 0 to 2 pi. So this, now let's take first x equals 1 and y equals 0. This is t equals to 0. Now let's take t equals pi over 2, which is 0 1. It's pi over 2. And then let's take 3 pi over 2, which is here. So negative 1 0. 3 pi over 2, and then basically this is 3 pi over 2, 0 negative 1, and it just goes back, t equals to 3 pi over 2, and here t equals to 2 pi. And now this is our circle. Now he's saying this is a semicircle, semicircle, and basically this is not a semicircle, except if it's from t bigger than or equal 0 or smaller than or equal pi. And so if it's like this, we're gonna say it's semicircle, yes. But if it's not, it's like this, it's gonna be a full circle, not semicircle. And so let's assume just it's from 0 to 2 pi, as he's saying, okay. And now since we draw this, now let's just find the work. So the work is basically, we said f of rt times dr over dt. So now let's plug in rt, and so yeah, so w equals the integral. Let's find first f of rt. Now this is basically minus y squared I. Okay, so we have in r, here we have this is x and this is y, and so minus y squared is just minus sine squared of t times I. Okay, and then x is just so plus cosine of t, and then y is just sine of t times j. So we took this x, this is our x, and we took this y, this is our y, and we substitute that back into f of x of y. And this is f of r of t. That's basically it. And now, as we have done this, we need also to find, so we found this f of r of t. Now we need to find dr over dt, which is very simple. So finding r prime of t, which is dr of dt, is just minus sine of t times I plus cosine of t times j. Now this is our derivative, and basically let's just do f of r of t dot r of t, which is basically multiplying the i's and adding it to the, and multiplying the j's and adding them together. So the i's multiplying them gonna give us, so minus minus is plus sine to the 3 of t, and here is gonna be just plus cosine squared t sine of t. That's basically our product. And so let's find the work. Work is equal to the integral of this sine of 3t plus cosine squared of t sine of t dt, of course, from 0 to 2 pi. Now we can evaluate this. It's relatively easy to do. So for this, we're gonna use the substitution rule. Now for the sine to the 3t, we might use a reduction formula, reduction of order formula. So this is basically can be reduction of order formula, sine. And so basically we could expand it to sine squared of t and cosine squared of t. Okay, and then we take the double angle identity sine squared and then we spread it out. So there is a way to do this. Yeah, so there is a way to do this, but it's gonna take some time. It's gonna involve some double sine squared identity, okay, which is sine squared equals half 1 minus cosine 2t, and then we're gonna multiply that by just sine, and we're gonna use some identities and also maybe substitution or integration by parts. And this is basically not the main topic here. Just our main topic is to find or be able to find the integral here. Okay, that's basically our integral. Okay, and now let's solve our second example. And so it wants us to find the work done by the force field, which is this field, over the curve r of t from t. Okay, and he gave us the points here from 0 to 1, 1, 1. Okay, and so now we could do this using this way. We can just do our regular way of integrating. Okay, so okay, let's try to do this. Now we have here first x equals to t, y equals to t squared, and z equals to t to the 3. And so now this, we will have x, y, z, and so we can substitute this into f of x, y, z, x, y. So yes, so f of x, y, so z is involved too. Okay, so f and then r of t, as you can see here and then here, and then we're gonna do t squared minus t squared times I plus t to the 3 minus t squared all squared, so t to the 4 j plus t minus t to the 3 also, so t to 6 to the 3, and then times k. And so this is 0 squared t squared, and then okay. And so this is basically just t to the 3 minus t to the 4 j plus t minus t to the 6. Is it t to the 6? Is t to the 6 times k. It's interesting. And now this is f of rt. Now let's find dr over dt. Now this, and so basically it's just I plus 2tj plus 3tk, 3t squared k. And so now basically the work is just integral of c f r of t, you can see dr over dt times dt. Now w is equal to the integral. Of course, we can find the dot product here. So f r of t dot dr over dt is gonna give us basically, so for the I is 0, for the j is gonna be 2t times t to the 3 minus t to the 4 plus 3t squared times t minus t to the 6. So 3t squared t minus t to the 6. And this can be further simplified to the following. So it can be done to t to the 4 minus 2t to the 5 plus 3t to the 3 minus 3t to the 9. Now this is basically our product, and so the work is going to equal the integral of c, the integral of this, which is 2t to the 4 minus 2t to the 5, 3t to the 3 dt. And this is from t equals 0 to 1. And so that's our work. And so if we want to integrate this, that's very simple. It's gonna be 2 over 5 t to the 5 minus 1 over 3 t to the 6 plus 3 over 4 t to the 4 minus 3 over 10 t to the 10 evaluated from 0 to 1, which is gonna give us basically 2 over 5 minus 1 over 3 plus 3 over 4 minus 3 over 10, and this can be evaluated very easily with 0 of course, and we can find this value. That's basically our work. Now by this we can find our work, and now let's see what's this. So that's our example that we just solved. Now r of t equals ti plus t squared j plus t to the 3k, and it starts from the point 0, 0, 0 up to 1, 1, 1, and here as you can see the projection of the point in the xy plane is 1, 1, 0. So the curve in example 4 is just this, that's the curve, and we basically found the length of that curve, you could say, the length of that curve, which is the line integral. Okay, and we basically found this length, which is very interesting. We were able to find the length of various functions over this field, as you can see, so which is very interesting and nice to be able to do. Okay, next up. So this is the work done by a force F and the line integral of scalar component f dot t over the smooth curve from A to B. Okay, that's another example. This is t, this is f. Okay, and t is just the change of the distance, which is the velocity. And now here, as you can see, that these are different ways to write the work integral for our example. So if we have f equals mi, nj, and pt over this curve, it can be written in different ways. This is one. All of these ways are possible to solve the same question. Okay, now moving on to the flow. Let's define the flow. If r of t is a curve parameterized velocity field curve, now the flow is from A to B. Okay, so the flow basically is defined by flow integral of cf dot t ds, and the integral is called a flow integral. And there is here a quick note which says that if a curve starts and ends at the same point, so A equals B, the flow is called circulation around the curve. So maybe it's something like this, goes back, so it's like this, Okay, and goes back. So this A, this B. Interesting. This is the flow integral. Now, let's try to find the flow of some example here. Now, okay, let's find the flow. So we need to find first. We'll not need to find anything really, will we? So it's f dot t, basically simply f dot t. So f of r of t is gonna equal to, now x equals this, y equals this, z equals this. So we have cosine of t, I plus tj plus sine of tk. And we have dr over dt, which is basically minus sine of t, I plus cosine of t, j plus k. And the dot product of these two is just r of t dot dr for dt, which is equals to cosine of t sine of t with a minus sign plus t cosine of t plus sine of t. Now the flow is just from 0 to pi over 2. It's the integral of cosine of t sine of t plus t cosine of t plus sine of t dt. Now this is simple integration, this is integration by parts, and this is simple substitution. We can find the flow easily. And so let's say example 4. So he wants us to find the circulation of the field. Okay, so this is the circulation around the circle, and from 0 to 2 pi, so we're gonna circle around, okay. And he wants us to find basically the flow. The circulation, we said, is just the curve starts and ends at the same point as the circulation. And so we can check if this is a circulation by just substituting 0 here. Okay. So if we put 0, this is 1 plus 0. And if we put 2 pi, it's gonna be 1 plus 0. So it's, you can say it's a circulation. Okay. From A to B over the curve. Now, basically, let's do the same. R of t equals x equals cosine, y equals sine, cosine of t minus sine of t, I plus cosine of t, j. Now, this is flow, so we have dr over dt is gonna equal to cosine, so the derivative, so minus sine of t, I plus cosine of t, j. And so let's do the dot product. r dot t dot dr over dt is gonna give us basically minus sine of t cosine of t minus sine of t plus cosine squared of t. And basically the flow is the integral of this. Integral from 0 to 2 pi of sine squared of t minus sine of t cosine t. Okay, and now this is basically 1. Sine squared plus cosine squared equals 1. So plus 1, so this is basically integral from 0 to 2 pi of 1 minus sine of t cosine of t. This way let u equals to sine of t and du equals cosine of t dt. And so it's basically t minus u squared over 2, which is sine squared of t over 2 from 0 to 2 pi. And that's how we find our, and this is just gonna be 2 pi. Okay, now as you can see this is a vector field curve r of t. Okay, so now we're gonna cover vector fields. Okay, so we're gonna cover vector field. So we have here a circle. It looks like the curve r of t, yes, and we can see the vector field in the green. This is our vector field, and so we can, as you can see, these are also different curves. So they are curves that are, simple but not closed, and they are curves that are also simple and closed. So these are, the simple curves are just regular curves that don't intersect. So like this, something like this. They don't intersect themselves two times. However, not simple curves or complex curves can intersect themselves. Okay, and so it's gonna be this, come this. These are some examples of not simple curves. And so closed curves can be loops also. And now let's define the flux. What is the flux? So definition. If C is a small simple closed curve in the domain of a continuous vector field f equals m of xy plus n of xy in the plane. Okay, so this is our vector field, as you can see. And we have also n, which is an outward unit vector, normal to, outward pointing unit vector on C. Okay, so it's a normal unit vector. The flux is basically across C is this. Flux is gonna equal the integral over the curve f dot n, f dot the vector n, ds. That's basically our flux. Let's look closely at this. So for a clockwise motion, we have k cross t points outward. So as you can see, as you know, if you have taken physics, the flux is highly dependent on the basically the direction of the motion. Is it clockwise, counterclockwise, etc. So we have here, for example, k cross t. Now k cross t is a vector that's pointing outward, out of the curve. Okay, you could say it's pointing from the center of the loop here and out of it. And so, as you can see here, that's for clockwise motion. See, this is clockwise. It points outward. Okay, and that's the product k cross t. Now if we do t cross k, it's gonna point inward. And so now here if we take counterclockwise, the product t cross k, not k cross t. Our first example is k cross t. Now t cross k is gonna give us a vector which is also pointing upward because we reverse the order of the cross product. So, but if we have k cross t, as in our first example, the vector is gonna be basically pointing inwards, which is k cross t. Okay, and in order to find an outward unit vector, transverse, okay, we need to take n equals t cross k. In the clockwise motion, we're gonna take n equals t cross k. Okay. For a clockwise motion, we're gonna take n equals k cross t. And we need to make sure in order to get our n, which is an outward pointing unit vector, we need to get that. And so to get that, we need to make sure that, yeah, we need to know what is the direction of the flow, and also we need to choose our cross product. So is it t cross k or k cross t? And that's basically how we do it. That's calculating the flux across a smooth closed plane curve. So the flux can be calculated. So this is, say, a symbol for the flux. So m dy minus n dx. Okay. So and can be evaluated for any smooth parameterization. T bigger than a and smaller than b. And that c counterclockwise traces it exactly once. And that's basically our flux. Now let's solve an example. Solve an example, as you can see here. Okay, so we want to find the flux. So this is M. Okay, so we have first the force field, okay, and we want to identify M and N and also X and Y. And so basically M is this and N is this. Okay, and we do have N. Okay, yeah. So flux equals the integral of M, which is X minus Y, minus N, which is X dx. And so now if we want to find dy or dx, we can find it through this equation. Okay, so this is the flux and we want to find it now. So do you have a function of t? We don't have a function of t. Now we could make a function of t out of this, which is basically x equals cosine of t, y equals sine of t, dx equals minus sine of t, dt, and dy equals cosine of t, dt. Now here we just substitute the values. So flux equals the integral of cosine of t minus sine of t dy, so it's cosine of t, and then minus x cosine of t dx is just, so let's just remove this. Yeah, and then dy equals cosine of t dt, and dx is just, okay, so dt minus cosine of t and dx is just minus, so we're gonna have plus sine of t dt, and we can take dt as a common factor, so flux equals the integral of cosine squared of t minus sine of t cosine of t plus sine of t cosine of t dt, and these are going to cancel, and so we'll be left with cosine squared of t dt, which is basically integral of 1 over 2 1 plus cosine 2t. This is very easy to integrate. Of course, the limits here are gonna be over the closed curve, so it's gonna be from 0 to 2 pi. Okay, so we're gonna trace it once only, and so 1 over 2 t plus 1 over 2 sine of 2t, so cosine of 2t times 2 from 0 to 2 pi, which is equal to, so 2 pi is just 0, so 1 over 2 times 2 pi minus 0, which is just pi. And that's our flux. And that's it. Thank you for watching. We covered everything for this chapter.